This video is on the Fundamental Theorem of Calculus, Part 1, which actually relates the two sort of halves of calculus. One is the definite integral, that's the signed area under a curve, and the other is the derivative. So assume that f is a continuous function on a to b. If f is an antiderivative of f on a to b, in other words, the derivative of capital F is lowercase f on that interval, then the signed area under the curve from a to b of lowercase f is capital F evaluated at b minus capital F evaluated at a. And that is not only maybe a little bit surprising, but it's also really useful. So it's a little strong to call this a proof, but let's say why. Why should you believe that's true? Well, do you remember the mean value theorem? The mean value theorem basically said if you have a function and you have its average rate of change, there's some place where its derivative is equal to that average rate of change. So let's think about capital F, okay? And capital F sort of we're concerned about its value all the way from B to A, but let's sort of think about this height as being F, or maybe I should say, there are a bunch of intervals here. Let's say this is xi to xi plus 1, okay? And let's think about the function capital F. So if capital F is going between these 2 points, the mean value theorem says there's some point f prime where you can take the derivative and it's equal to f of xi plus 1 minus f of xi over the change, and we call that delta x. Well, think about that. What is the derivative of capital F? That is actually lowercase f. So really what we're saying here is that this difference, right, f xi plus 1 minus f of xi equals lowercase f of ci, some c in that interval, times delta x. And if you go back and look at the definition of the definite integral, right, this piece here will actually be, you are summing more and more of these to get to that piece, okay? So that's actually perhaps a sense of why this is true. But why is it so useful? I mean, maybe that's even more important. Let's think about this. If I'm trying to find the signed area under the curve x squared plus 2, first off, what I do is I just figure out something whose derivative is x squared plus 2. X to the third, 1 over 3. That's derivative will be x squared plus 2x. Now I need to, if that's my function capital F, I need to evaluate that at 3 and subtract 1. That's how we write it usually. Now I plug 3 into that. So 1/3, 3 to the third, plus 2 times 3. All that minus 1 plugged into that same thing. 1/3 times 1 to the third plus 2 times 1. So what I actually get out is 27 plus 6 minus 1/3 minus 2. So let's say minus 1/3 minus 2. So you could then say, that's something like 30 2/3.